Okay, hey, looks like pretty much, well, most folks are here. So let me make sure the doc cam is fired up and we can pick up where we left off last time. All right. So according to my notes, we were just about to talk about vertical tangent lines. So lately we've been discussing the derivative as a function and talking a little bit about how to sketch the graph of the derivative given the graph of the original function. I want to continue along those lines, and most of your homework problems this week are that sort of problem. A word of warning, so here, let's do the thing. So we're learning how to sketch f prime from the graph of f. I'll, getting a little more sun in now than I was earlier this morning, so I'll readjust the camera a little bit. A warning. We must draw the graphs by hand as you work the homework problems. Guessing in WebAssign may get the homework done, but you won't learn anything from it. I'm doing that. So if you want to learn this stuff, and believe me when I say section 2.8, this is one of those important sections where you will start to make connections. In order to get what you need to get out of this, you gotta do the thing like we're doing it in lecture, where you look at the graph of f and you make a few guesses at the slopes of the tangent and you start to sketch f prime from that. If you just go through the homework like guessing this graph, that graph, oh, that's wrong, I'll switch to this one, you're not going to get everything out of the homework that you're intended to get out of the homework, and that will show on the exam. All right? I want you guys to do well. I know that oftentimes the homework feels like a lot and you just want to get it done. But remember, that's really where you're going to be gaining these skills. I could show you how to hula hoop. Okay, full disclosure, I couldn't show you how to hula hoop, but my wife could show you how to hula hoop. Could show you how to hula hoop. You could watch me hula hoop all day. You could pick out from a collection of pictures or videos what good hula hooping technique looks like. But until you put the thing around your waist and start fiddling with it, you're not going to have any idea how to actually hula hoop. The analogy works well here. I can show you how to select the graph of f prime. I can show you how to draw the graph of f prime. And you can go in and effectively guess and use the process of elimination to answer the homework questions related to this section correctly. But then on the exam, when I tell you to draw a graph, you're gonna be in trouble because you won't have practiced the skill. So as you work through this week's homework, make sure you're giving it the respect it deserves. And what that means specifically for these problems is draw the graphs by hand. Copy the graph of f, and then try to sketch the graph of f prime, following the procedure that we've been using in class, and you will be okay. All right, so I just want to say, this is one of those things, when I teach these classes in person, I don't usually do online homework. I usually do it all paper, and I have people hand things in so I can grade them, and that way I can look at your graph sketches and all the little details that we can't see online. In this era of COVID, that's not an option. So we have to do it through WebAssign, but that means I really need you guys to be responsible and mature about it. There's this term mathematical maturity, which is not like the same thing as regular maturity, but it's similar in the sense that you being really honest with yourself about what you've comprehended and what you haven't, and what you've done and what you haven't, and you're not trying to fib to yourself or to anybody else about what your skills are. You need to be mathematically mature to make it through this class and get out what you need to. Okay, so with that caveat, I want to pick up where we left off last time. So let's look at see if we can sketch the graph of f primed of x, where f of x is x to the 2/3 power. This function, you might not even know what the graph of this guy looks like, depending on how good your pre-calc class was and how much time you guys spent on these things. I'm going to walk you through it gently. First, we're going to sketch the graph of f, and we're not going to use Desmos for this. This is a power function. We should be able to do this. Two ways you could think about it. That's either the cube root of x all squared, or the cube root of x squared. Both are correct. Both are the same as x to the 2/3. I claim that this is an even function. Because if I replace this x by negative x, then square that, it will be the same as the original here. So we expect y-axis symmetry. So f of x's graph will have y-axis symmetry. And maybe you remember from your algebra classes that the graph of a power function in quadrant 1, if the power is between 0 and 1, looks like the square root function. So that shape, together with knowing that f is an even function, is enough to give me the whole graph. Because f is even, its graph will have y-axis symmetry. So this is what the graph of f looks like. Some points that we know must be on here are like 1, 1. And because it's an even function, therefore -1, 1 has to be on there. If you like, another point that must be on the graph is 8, 4. And -8, 4. I get that by plugging 8 in here. The cube root of 8 is 2, 2 squared is 4. So this is a good graph of the original function f. And the question is, how can I get a good graph of the derivative? Well, I take these points, just a few points on the graph of f, and I estimate the slope of the tangent line. So over here, the slope is definitely negative, but it's not very steep, right? Like a -1 slope would look like this. So this is like maybe a -1/2 slope. If I look right here, this is like a -1 slope, right? If you imagine the tangent line in here, It's sloped negatively because we're going down as we go to the right, and it's more steep than it is over here. We can estimate that slope to be like -1. Over here, the slope, you could use a symmetry argument. The slope here is positive. And because the graph is symmetric, I should say the slope there is about +1. And over here, the slope is about +1/2. And then one other observation I would like to make before we try to sketch the graph of f primed. Yes, you could, but the point here is to sketch the graph of f primed without knowing the formula for f prime. So if you have a formula for f prime, if you take the derivative, then of course you can use that to draw the graph of the derivative. But the point here is to learn the geometry, is to learn how to visualize the graph of the derivative given the graph of the original. And there are a number of homework problems you have where I just give you the graph. I don't give you any algebra for the function, either the original or the derivative. So you need to be able to do this. The other observation I would like to make is that as you get close to 0 here, for x just to the left of x equals 0, the tangent line, the slope of the tangent is huge and negative, right? Like if I took an x value right here, that tangent line is very, very steep and very, very negative. Yeah, let's say I take the tangent line right here. Looks kind of like that, right? Very, very steep and negative. So for x is just to the left of 0, the slope of the tangent line is huge and negative. This means f prime has, I'll write it in the goes to notation, goes to -infinity as x goes to 0 from the left. Right? If I get closer and closer to 0, these tangent lines are getting steeper and steeper and steeper. Similarly, for x's just to the right of x equals 0, the slope of the tangent line is huge and positive, right? Like imagine I take a point like right here, then my tangent line there would look like this, which is very, very steep and positive. And if I get closer and closer to 0 from the right, that tangent line gets more and more steep. You can think of a vertical line as being a line with infinite slope. So here we would say, therefore, f primed of x goes to +infinity as x goes to 0 from the right. So I want to take a second and make sure you guys are comfortable with these observations, approximations, the graph of f that we cooked up. Questions about any of this?
Are you gonna give examples of ones that like don't go off into infinity or anything like that?
Yeah. Well, if you look at what we did in our last class, that we did several examples like that, and I can do another example along those lines. So yeah, if we want to, as a recap towards the end of the day today, we can do some other examples like that. I've got one more example in line after this, that involves vertical tangents, so things going f prime going to infinity. So let's see if we can't sketch the graph of f primed. Remember how we do this. When x is -8, the slope is like -1/2. So I'll try to make this look similarly scaled. We'll call this 1. So when x is equal to -8 here, at this point, the slope was -1/2. So that would put me somewhere right around here. That's the point. So on the graph of f primed of x, I'm going to list some points over here. -8, comma, the slope there, which was -1/2. -1, comma, the slope there, which was -1. 1, comma, 1, because the slope at x equals 1 was 1, and 8, comma, +1/2, because the slope there looked to be about 1/2. So here's 8, comma, -1/2. Here's -1, comma, 1, or -1, comma, -1. Here's 1, comma, 1, and here's 8, comma, 1/2. The other observation that we had was that f of x goes to -infinity as x goes to 0 from the left. So f primed goes to -infinity as x goes to 0 from the left. So the graph of f primed is going to have a vertical asymptote down here. And then you can kind of start to see the shape of the graph, right? Something like this over there. And also, f primed goes to +infinity as x goes to 0 from the right. So on the graph of f primed, we're shooting up to +infinity as x goes to 0 from the right. And from that, you can kind of see the shape of the graph over here. So this is a good picture of the graph of f primed, coming just from the graph of f. And I want you guys to look at those two graphs and try to understand what's coming from where. This point right here, where the tangent lines are getting very, very, very steep, corresponds to a vertical asymptote on the graph of f primed. Because very, very, very steep tangent lines have like infinite slope. Yes. Yep, so we're starting with the graph of the original function f, and we use that graph to sketch f primed. The way we figure out what f primed looks like is by looking at the original graph, picking a few points, and guessing the slope there. Those slopes will be y values on the graph of the derivative. The x values from these points are the x values of the points I started with. And then the y values of these points are the slopes of the tangent lines, because that's what the derivative returns, remember, is always the slope of the tangent line. In other words, the points on the graph of f primed are of the form some number a, comma, the slope of the tangent to f of x at x equals a, or just a, comma, f primed of a. Right, that's the idea. And the thing I'm trying to show you with this particular example is that this sort of behavior, a very, very pointy point, not just like a corner, like on the absolute value, but a place where the graph comes together to form a very sharp point, these are called cusps. Those give vertical asymptotes on the graph of the derivative, because the tangent lines at a cusp are vertical, i.e. the slope of the tangent line there is infinite. So note, yeah, points on the graph of f prime are of the form some number, comma, the slope of the tangent to the original at that number. Oh, so how am I guessing the slope of the tangent line? Well, I just imagine what the tangent line looks like right here. That line, to me, the tangent line right here, looks like it definitely has a negative slope, but it's shallow. It's not as steep as -1. -1 slope there would look like this. It's more like this. So I guess that the slope there is like -1/2. It's not a perfect science. The idea is that we're just trying to get the shape of the graph of f prime. It doesn't have to be perfect. So here I guess that the tangent line, if I set this down, that looks like a slope of like -1/2, right? It's definitely negative. It's definitely not as negative as like -1. The slope of -1 would look more like this. So I guess that it's -1/2. Could be -1/3, could be -0.2, could be -0.4, just a guess. Yeah, here we're more steep, right? So I guess that this guy has a slope of like -1. And that's where this point, -1, -1 is coming from. When x is -1, the graph of the original appears to have a tangent line whose slope is -1. If I wanted to come in a little bit further, I could say maybe the point 1/2, -4, or 1/2, -2 is on the derivative. Because here the tangent line a little bit closer looks like it's -2. And the closer I come to 0, the more steep that tangent line gets. There are always negative slopes, but the slopes are getting closer and closer to infinity. The line is getting closer and closer to vertical. So the graph of my derivative is going off to -infinity. And then the same sort of logic applies over here. If I look very, very close to x equals 0, but on the right-hand side, the slope is extremely steep and positive. That's like up here, right? Large positive number corresponding to the large positive slope. And then when I look at x equals 1, the slope there, this looks like a slope of about 1 to me. So I say, okay, well, when x is equal to 1, the slope on the original is about 1, so the point 1, 1's got to be on f prime's graph. If I come further out, that slope's still positive, but much less large. Maybe the slope here is like 1/2, so the point 8, 1/2 is on the derivative. The fact that you see the graph of f leveling out as you go further and further from 0 corresponds to the horizontal asymptote on f prime. And the cusp, where the slopes are like infinitely steep, correspond to the vertical asymptote on f prime. So that's my next note here. Cusps, which are like sharp, pointy bits on the graph of f, correspond to vertical asymptotes on the graph of f primed. So this is a place where you have vertical tangent lines. These cusps, these short pointy bits, these are places where the tangent line becomes vertical. Cool, okay, I'm glad. Yeah, there are these great moments, these wonderful click moments where the shit just starts to make sense. It's really good. We should reinforce that by doing another example. Before I move on, are there questions about these notes, these observations? Or any questions about how I got this graph from this graph? I don't want to distract, but it's worth mentioning. I can't resist mentioning because it is kind of my whole life. The research that I did in additive number theory is all about finding polynomial approximations to functions around cusps. That's basically the game. The polynomials are hypergeometric and built out of trig functions. But these things, cusps here, these are very interesting mathematical objects. And you'll see if you go on to take higher physics classes or higher math classes, they show up in interesting ways and do funny things. All right, let's look at another problem that involves vertical tangent lines. Same business. I'm going to sketch the graph of f of x, and this time I'm going to just go with the straight cube root of x and use it to sketch the graph of f primed. So the graph of the cube root function is another one of these power functions. We should know what that looks like. This one is an odd function. Over here, he looks like this. And over here, he looks like that. Again, it's not a perfect arc, but some points that are always on this sumbitch. (1, 1, -1, -1), and I'll extend a little bit further so we can get a few more. I'll call this 8. This would be 8, 2. Call this -8. This right here would be -8, -2. Okay, there's the cube root function. That's the original. That's f of x. It's a graph we should know. If you don't remember the graphs of those basic functions, go back through your algebra notes or look at the resources I've posted in Canvas under the modules page. There's lots of basics of graphing there. Or come by office hours and have a chat with me about the basic functions you should know and how to graph them. But make sure you get to a place where you can draw those graphs. Now we want to estimate the slopes at a few of these points so that we can try to draw the graph of f primed. Here, the slope is small and positive, maybe 1/3. Here, the slope is a little bit bigger and positive. I'll say that's like slope 1. I'm just estimating. Here, the slope is the same as the slope is here. So I'll say that's also 1. And here, the slope is the same as it is there. So I'll say that's 1/3, right? You can picture these tangent lines. Something like that. So the points on the graph of f prime this will be -8, 1/3. Sorry, that's a 3. -1, 1, 1, 1, and 8, 1/3. Okay. The other thing I'd like to do here is observe that as x goes to 0 from the left, f prime of x, the slope of the tangent line here, this is an extremely large positive slope. Right here at 0, we actually have a perfectly vertical tangent line. But just to the left of that, down here, I have a very, very large positive slope tangent line. So this is going to plus infinity. And that as x goes to 0 from the right, if I look just to the right over here, also large positive slope. So f primed is going to plus infinity there also. So together with those points and these observations about what happens near the vertical tangent line, I can draw a very nice graph of f primed. I'm going to have to shift it over here to get space for everything. Okay, we'll call this -1, we'll call this -8, we'll call this 1, we'll call this 8. 8 comma positive 1/3, I'll mark this as like 1 and this is like -1. So 8 comma positive 1/3 is like right here. -8 comma positive 1/3. -1 comma 1 is like up here. 1 comma 1 is like right here, and positive 8 comma 1/3 is like right here. And then this, as I approach 0 from the left, f primed is going up to plus infinity. And as I approach 0 from the right, f primed is going up to plus infinity. So the graph of f primed, in this case, has to look something like this. And it's going way up, all the way up to infinity here, right? And again, these don't have to be perfect works of art. We're beginning by making guesses anyway. But the important thing is that the shape is correct. That you've got asymptotes and intercepts where they belong, and that the shape is correct. That's the big thing here. So I hope you're seeing, if I were to look way out here on the graph of the original, the slope of the tangent would be positive, but it would be very, very, very small. Which is why the graph of the derivative gets very, very, very small, but stays positive as you wander off to the left, i.e. has a horizontal asymptote, y equals 0. And then as you walk along the graph of f, the slopes are getting more and more large. They stay positive, so this graph is always above the x-axis, and they're getting larger and larger. So this is getting bigger and bigger. And as you get close to 0, the slopes go off to infinity, because here you have a very briefly vertical tangent line. And then as you move past 0 on the right, the slopes are still positive and huge. So we're coming back up here with positive huge values. But then they start to get more shallow. So the derivative gets smaller, more shallow, derivative gets smaller. And as you wander very, very far off to this way, the tangent lines are almost horizontal. So as you wander very, very far off this way, f primed is getting closer and closer and closer to 0. Just for fun, let's see if Desmos agrees with us. I'll do the cube root first. Boom, look at that. The red is the original, f, and we knew what he looked like. We could be confident with that. That's this. And the blue is the derivative. And indeed, he's got the vertical asymptote at 0, he's got a horizontal asymptote, y equals 0, and he's got this shape that we showed. So anywhere you look along the red graph, right here, for example, the blue graph's y value will be the slope of the red graph's tangent line. This is how a function's graph is related to its derivative. And this is 80% of your homework this week, just this game. The other bit that you're learning this week is how to actually calculate the blue function without all that limit bullshit. Let me see, actually, I gotta remind myself whether I shoved that in there or not. So my notes here don't have it. I do say we want to get to 3.1. Let me see what I gave you. So all of this, right? Guessing the graph of f prime from the graph of f. All this same stuff. And then these problems here, find the derivative using the definition of the derivative. I guess we should do a few of those next because this is all using limits. Identify where f is not differentiable. We talked about this last time, right? You're not differentiable at any pointy bits or at any discontinuities. More identifying from the picture, using definitions. Okay, and then we're getting into this stuff. So I need to say something about this. Up through question 21, I'm going to come back to our notes here. So I want you guys to write this down. So that's the end of this example. On homework 4, for questions 1 through 21, whenever you're asked to calculate a derivative, you must use the limit definition. So read the questions. The question says use the definition. That is the limit as h goes to 0, f of x plus h minus f of x all over h. Not any other rules. Or tricks. And you might be saying, but John, we don't know any other rules or tricks. That's true. If this is your first time taking calc, but I get a lot of emails and questions saying, hey, I know a faster way to do this. Can I do that? For questions 1 through 21, the answer is no. You must use this. Those questions are only there to give you practice with this. That's their purpose. However, I am going to be teaching you guys some faster ways to calculate derivatives, and we're going to do that this week. These are piling up in the same homework because of the time we lost to Labor Day last week. Normally I would separate these. So please heed this rule, this warning. For the first 21 questions, most of them are look at the picture, sketch the graph of f prime, right? That's the stuff we just did. But a handful of them also say use the definition of the derivative to calculate f prime. I'm going to do one of those for you now. And on all of those, anytime it says use the definition, this is what they mean. If you do something else, especially if you do something else on an exam, if I say use the definition to calculate the derivative and you don't use this limit, you try some other differentiation tricks or tools, 0 credit. So this is important. I think Ali earlier asked to see if we could do another one of these curve sketching, like derivative sketching problems where we don't have any vertical tangent lines, but it seems like maybe a little bit of time we've practiced on this. Are you still feeling that way, or can we move on, or would we like to do one more of these where there isn't a vertical tangent?
We can move on.
Alrighty then, let's do that. So there's plenty of problems in your homework that say calculate f prime using the definition. Let's do a couple. We'll do a couple together, all right? Where's the first one? This one, I trust you guys can handle on your own. I'm not gonna spoil this one for you. Somebody in chat actually mentioned this the other day, right? When we were talking about the relationships between the degrees, like quadratic differentiates to linear, linear would differentiate to what? Here you answer that question in totality. What is the derivative of any linear function? The next guy is this one. I won't spoil this for you. He's not too hard. You just have to be patient and follow your nose. But this one requires a trick. So let me show you number 14. So they tell me g of t is 3 over the square root of t. And they want us to calculate g prime using the definition of the derivative. Okay, that means I need to calculate the limit. So g primed of t is the limit as h goes to 0, g of t plus h minus g of t all over h. I'm going to plug in. So that's the limit as h goes to 0, g of t plus h is 3 over the square root of t plus h. So you got to get your function notation stuff right. Yeah, the t plus h has to go inside the function. So it's 3 over the square root of t plus h minus g of t is 3 over the square root of t. And then we divide this whole apparatus by h. The problem with just sending h to 0 right away is that I've got a 0 in the denominator. That's no good. So I need to do some algebra. First step for me would be to have a common denominator between these two. And maybe also to write this whole divide by h as a multiply by 1 over h. So I'll have limit h to 0. And please, when you're doing these, be good with your notation. Keep everything nice and clear. Don't skip writing limits or equal signs where they belong. I'll write the whole divide by h thing as a 1 over h. And then upstairs there, I need to have a common denominator. So this first piece I'll treat as it's 3 over t plus h. But then if I want to have a common denominator between these, I need to multiply by root t over root t. And then minus 3 over root t. And again, if I want a common denominator, I have to multiply this guy up and down by this guy's denominator. So he'll get multiplied by root t plus h over root t plus h. Questions so far?
So you just basically took the h from the bottom and pulled it out front.
Yes, exactly. Yeah, this h, dividing all this shit by h is the same as multiplying all that shit by 1 over h. And then I've got this minus this. But in order to get a common denominator, I need to multiply this by the piece his denominator is missing, which is the root t. But if I'm going to multiply by root t downstairs, I got to do it upstairs. So here's that 3 over root t plus h with the piece that it needs to have a common denominator multiplied. And here's the 3 over root t with the piece it needs to have the common denominator multiplied. Everybody sees where these are coming from? So this will be 3 square root of t minus 3 square root of t plus h over square root of t times the square root of t plus h. All right, and these are multiplied down here. I'll make that clear. I still have the issue with an h downstairs. Can't send h to 0 yet. But let me rewrite this as a single fraction so that it looks a little prettier. And then we'll see if anybody spots a trick that we could use. I can factor a 3 out from the top. Let me do that also. So I'll have 3 times square root t minus square root t plus h all over h times root t times root t plus h. we've seen this sort of situation before, right? Where I've got like a square root minus a square root, and I can't take the limit yet because the bottom goes to 0. How did we handle those in the past?
Multiplied by the conjugate.
Beautiful, we multiply by the conjugate. The conjugate of the numerator is what you get when you swap this minus for a plus. So I'm going to multiply top and bottom by root t plus h. So I'll have lim h to 0, 3 times root t minus root t plus h over h root t plus h times the conjugate, which is root t plus root t plus h. So this is that multiply by the conjugate trick again. And of course, I think of this like this. Fractions are grouping symbols. And the magic is that if I FOIL out the top, something cool will happen. Leave the 3 alone, but FOIL these. Think along with me here, and then I'll give you time to write things down. My firsts are the square root of t times the square root of t. That's the square root of t squared. That's just t. That's my first. My outers are square root of t times square root of t plus h. And my inners are square root of t times negative square root of t plus h. These cancel. Maybe I'll write that. Plus root t times root t plus h. There's my first outer, and then root t minus root t times root t plus h. There's my inner. And then my lasts are negative root t plus h times positive root t plus h. That's negative root t plus h times root t plus h, or negative root t plus h squared. That's negative t plus h. So there's the top FOILed. And the bottom is h root t plus h times root t plus root t plus h, like so. And the nice thing is that the middle terms add up to 0. These add up to 0. You see it? It's plus something minus that same thing. So these guys sum to 0. And what's left is t minus parentheses t plus h. So this is lim h to 0, 3 times, I'll write it, t minus h over this big denominator, h root t plus h root t plus h. Of course, these add up to 0. So you get lim h to 0, negative 3h upstairs, divided by this monstrous denominator h root t plus h, parentheses root t plus h. And now we can finally cancel the h, boom, boom, from the denominator. So I'll have lim h to 0, negative 3 over root t times root t plus h times root t plus root t plus h. Finally, now that the factor of h is gone from the denominator, I can send h to 0 and get -3 over, this will be root t, this will be root t. This will be root t, this will be root t. So what is that? Downstairs here, this is root t times root t, that's t. So this is -3 over t times, and this is root t plus root t, 2 square roots of t. Or if you really want, you could write it as -3/2 times 1 over t. Well, let's see, this is t to the 1, this is t to the 1/2. So that's going to be t to the 1 plus 1/2 downstairs is t to the 3/2 downstairs. This is t to the -3/2. All right, you could stop here if you wanted to. I wouldn't request or require you simplify to this. But for those who know the tricks, this should look familiar. Now, those tricks are only good if you understand where they come from and why they work. Trick doesn't mean shit if you can't back it up. This is how you back it up. I know that there's a lot of algebra here, so I want to make sure we're all comfy with what we did, why we did it, where it came from, where it went. So take a second to look over your notes and make sure they agree with mine. And then if you have questions about any one step after you've reviewed all your notes and you're sure everything looks correct, ask them. Okay, questions? Any one of these lines, any one of these steps. I really want to know what you guys are thinking.
I have a quick question.
Yeah.
The answer would be -3/2 with the t or without it at the end?
Here.
Yes.
So the 3 is coming from this and the 2 is coming from this. And the whole thing, -3/2, is multiplying the t to the -3/2.
That would be it.
Yep.
Oh, okay. I just
Yeah, that's it. That is g primed of t.
Gotcha. Thank you.
Other questions? Okay. So we've already made one big step here this week, and that is going from thinking about the derivative as like a number that you find one at a time to thinking about it as a function. That's a big step, and understanding the graph of the derivative as it relates to the graph of the original, probably the most important thing in the first half of this class. The next thing I need to teach you how to do is calculate derivatives of exponential functions. We haven't actually fucked with those at all yet. And you remember from your algebra classes, everybody is all like, ooh, exponential functions, they're so awesome, yay. Why? But why though? So let me show you. Again, I don't want to move from this until we're sure we're comfy with it. So are there any other questions on this process? It's a long problem. I will make you do shit like this on the test. You will have to show work. So if you have questions, this is a good time to ask them.
I have one more question.
Yes, please.
Would it be like a study guide to practice for the exam?
So the study guide is going to be a set of problems that are about exam level difficulty. I'll release it 1 week before the test. So the day we finish covering the material for exam 1 is the day I will release the study guide. We're a little bit behind due to the holiday, but if you look at our syllabus, right, normally exam 1 would be next week, which would mean I would release the study guide this week. However, you see, we're still back here. We're just about to start this, which means probably the exam is not next week. The exam will be the week after. And I'll release the study guide either Wednesday or Friday of next week. And the exam will be Wednesday or Friday of the following week, depending on how long it takes us to get through these next few sections.
Okay.
The study guide is not super long. It's not comprehensive of every single thing you could say on the test. It's just a handful of the most important problems. And then I have you write out your solutions and share them with me so we can talk before the exam about your work. So the next thing I want to do, something we haven't touched yet, is explore derivatives of exponential functions. Which means we're going to run into that number e. In fact, we're going to start by playing around with the function e to the x. So pretend you don't know what e, which again is like 2.71828 blah, 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 is. It's just a number. If f of x is e to the x, then f primed of x would be the limit as h goes to 0, f of x plus h minus f of x all over h, right? Well, if f of x is e to the x, then what is f of x plus h? Don't leave me hanging on that one. If f of x is e to the x, then what is f of x plus h?
E to the x plus h.
Right. Yeah, and it's all in the exponent, right? E to the x plus h, like this. And then minus f of x would mean minus e to the x, and all of this is divided by h. And if you remember your rules for exponents, e to the x plus h is e to the x times e to the h. So my numerator here is e to the x minus times e to the h minus e to the x all over h. And you can factor e to the x out. like so. Everybody see it? If I factor e to the x out, this piece becomes e to the h, and this piece just becomes 1. And a neat thing that's going on here, this limit is sending h to 0. This piece doesn't have any h's in it, so I can actually bring him outside the limit. So this is equal to e to the x times the limit as h goes to 0, e to the h minus 1 over h. So what we see here is that the derivative of e to the x is equal to e to the x times whatever this number comes out to be. And one way of defining the number e, and this is what your textbook does, I'm not crazy about it, but this is how your textbook handles this. They say the definition of the number e is the solution to lim h to 0 b to the h minus 1 over h equals 1. In other words, this limit, the limit as h goes to 0, e to the h minus 1 over h is 1. They take that to be the definition of the number e. It's not the definition that you see in your algebra classes, and so I'm not crazy about this approach. But this is one way to do things, and it is correct. It's just not super appealing. In other words, the derivative of f of x equals e to the x is f primed of x equals e to the x. This is a big deal. E to the x differentiates to e to the x. He's his own derivative. That's a big deal. That's why mathematicians are so into exponential functions. Because e to the x is his own derivative. In other words, the instantaneous rate of change, the slope of the tangent on the graph e to the x is the same as the y value there. So here's the graph e to the x. We'll mark this maybe as -1. This is clearly 0. And we'll mark this as 1. The slope of the tangent line here so here f of -1 is e to the -1, and f primed of -1 is e to the -1. F and f prime are the same for this function. So the slope of the tangent line here is 1 over e, or about 1/3. Right here at the at x equals 0, f of 0 is 1, and f primed of 0 is 1. The slope of the tangent line there is the same as the height of the point. Over here, f of 1 is e, and f primed of 1 is e. So e to the x is the unique function that is equal to its own derivative. It's the unique function such that the slope of the tangent line at any point is the same as the height of that point. So the height of this point is e, because I'm on the graph of e to the x and I've plugged in x equals 1. And the slope of the tangent line there is also e. This is a really nice feature for a function to have, especially if you're trying to do what are called differential equations, solve equations that are given in terms of the derivative of a function. And since physics is all written in differential equations, the nature of the physical world is that forces act on each other and forces are derivatives. So e to the x and exponentials in general are very, very nice to differentiate and hence to work with using calculus. I'm going to give you one more fact, and then I'm going to introduce some new notation. First, questions about what we've done and said here.
So the e to the x in front of the limit, you just ignore that and make it equal to 1, the limit?
Well, this piece is equal to 1.
He
Oh, so it's just
factored
e
it
of
out.
x.
So
Okay.
we get e to the x times 1. Yeah, so the e to the x here comes along for the ride. And this limit is equal to 1.
Okay.
So the derivative of e to the x, f primed, is e to the x times this limit, and that limit is 1. So f primed is just e to the x.
Okay. Thanks.
Yeah, good question. Other questions? All right. Another fact. So we just learned, or just discovered, that e to the x primed is e to the x. What about other bases? I'll be able to prove this for you a different way using the chain rule when we get to that, which will be next week. But if f of x is b to the x, then the same sort of work will show that f primed of x is b to the x times the limit as h goes to 0, b to the h minus 1 over h. It's the same work we did on the previous page, just with the letter b instead of the letter e. It turns out that in general, the limit h to 0, b to the h minus 1 over h, this is an h, this is the natural log of b. So f primed of x is b to the x times the natural log of b. And you see how e to the x fits into this. If b is the number e, then this would be e to the x times the natural log of e. Well, the natural log of e is 1. The derivative of any exponential function, a function like 2 to the x, 5 to the x, 1/3 to the x, will always be that function times the natural log of the base. Right? So you have this natural log of b floating around. In other words, let's do an example or two. If f of x is, let's do 3 to the x, then f primed of x would be 3 to the x times the natural log of 3. If f of x is 3 to the negative x, which is the same as 1 over 3 to the x, then f primed of x would be 1 over 3 to the x times the natural log of 1/3. Or if f of x is 1.234 to the x, then f primed of x would be 1.234 to the x times the natural log of 1.234. The way a mathematician would describe this relationship, we would say that exponential functions are proportional to their own derivatives. So the derivative is always the original function times some number. The original function times some number. The original function times some number. And remember, derivatives are growth rates. It's how fast the function is growing. It's the rate of change. So the rate of change for any exponential function is proportional to itself. The derivative of 3 to the x is 3 to the x times some constant, right? No x's here. So we'll talk more about this as we go down the line, but this property, the fact that e to the x differentiates to himself, is the main thing I want you to remember from this part of today's lecture, right? This is the one that really matters. I'll be able to prove this shit to you again in the future. I'll be able to prove this shit to you again in the future using the chain rule. For now, more than anything, I want you to remember that e to the x is its own derivative, right? All the graphing stuff we did at the start, super important, right? Probably the most important.
One thing, will we prove like basically the definition of E? Like using the first limit?
I don't intend to do that. That's actually a little bit more work than is appropriate for this class. It's, of course, perfectly doable. But what I will do is use the chain rule to prove this extension. So for us in this class, we take E to be defined by this limit. All right? We say by E is the number such that e to the h minus 1 over h has limit 1. That's the definition we use in the calc book. If you want to see how this relates to the definition that you've seen in your algebra classes, come by an office hour and we can run through that together. But it's a little bit distracting from what we're trying to do in this class, because what we're trying to do in this class is get you guys to a place where you can use calculus. Okay. So the big takeaway here is that the derivative of e to the x is e to the x. There's two other things I want to do with you this week. One of them is teach you some other notation. And then the other thing is to show you the first new differentiation rule besides this, and that's the power rule. I think explaining the new notation will be easier if you already have the power rule. So the next thing I'm going to do is show you this theorem. What I'm giving you now, you cannot use on the first 21 problems in the homework, right? Every time the first 21 problems of the homework ask you for a derivative, you need to calculate it using the limit. If you don't practice that, then when I ask you to do it on the test, it will bite you in the booty. But here's the deal. You can write it without the parens if you want it. It's p times x to the p minus 1. This is called the power rule. For derivatives. I'll do a quick example. Earlier, we looked at the problem of finding g prime, where g was 3 over the square root of t. I can rewrite that as 3 times t to the negative 1/2. And if I apply my power rule, the 3 is just going to come along for a ride, and then I'll get negative 1/2 times t to the negative 1/2 minus 1, which is negative 3/2 times t to the negative 3/2. How much faster is that? It's a lot faster. It's a shitload faster. Okay, so this power rule, I want to prove this to you, at least in the case where n is an integer. The proof, though, is going to require use of the binomial theorem, and I don't want to scare you too much. If f of x is x to the n, then f primed of x is the limit as h goes to 0, f of x plus h minus f of x all over h, which is the limit as h goes to 0 of x plus h to the n minus x to the n over h. The challenge here is dealing with this. You have to FOIL all this out, but you don't know what n is. N is an arbitrary positive integer here. Recall that x plus h to the n can be expanded using the binomial theorem as the sum from k equals 0 to n choose k, x to the n minus k times h to the k. The first few terms of which are x to the n plus n x to the n minus 1 times h, and then so on. Right, this is how that term starts, how that binomial theorem, binomial expansion looks. Here, all of the terms that this ends with, the last two terms here are x squared times h to the n minus 1, and then x times h to the n minus 1, and then h to the n. All of these in the dot dot dots have powers of h greater than 1. So if we take this information and bring it back here, we get the limit as h goes to 0 of x to the n plus x n x to the n minus 1 times h plus lower order terms, all of which contain powers of h. The second to last term is x times h to the n minus 1, and the last term is h to the n, minus x to the n, that's the minus x to the n that we had from the original bit, all over h. So this is my binomial theorem expansion of x plus h to the n. That piece is this piece. This piece, x to the n, is this piece. What you'll see is that the x to the n's add up to 0. They go away. And we'll get the limit as h goes to 0 of n x to the n minus 1 times h plus a bunch of other stuff that has h's in it plus x h to the n minus 1 plus h to the n all over h. And now when we factor h out from the top, we'll have h times n x to the n minus 1 plus a bunch of stuff with h's. All over h. You can cancel these, and you get lim h to 0 n x to the n minus 1 plus all that stuff with h's. All the stuff with the h's is going to go to 0 as h goes to 0. So you end up with just n x to the n minus 1 plus 0, or n x to the n minus 1. That's the proof of the power rule. So again, I don't want you using the power rule on the first 21 problems in the homework. If you do, you're cutting yourself out from some practice that you need to get working with these limits. Don't stress too much about the proof I've just shown you. You're not responsible for the proof. You are responsible for the theorem. You're responsible for knowing the power rule. And you see here the derivative of x to some power is that power times x to 1 power less, which is what we've just shown here. If you differentiate x to the n, you get n times x to the n minus 1. These two facts together, along with one little rule for the derivative, which I will show you next time, will be enough to differentiate not just any polynomial, but any linear combination of polynomials, power functions, and exponential functions. So for now, today, I would like you guys to go into the homework and solve problems up through 21. Try to get all those done. Don't use the power rule anywhere. Use the limit definition of the derivative, as we've been doing in class today. And then on Friday, I'm going to show you guys how to use this power rule to attack more and more problems and to get those answers fast, much, much faster than the methods you're using right now, the limits. That will be the beginning of chapter 3. That will be us starting on differentiation rules, which are like shortcuts for getting around that whole limit thing. But the limit thing is important. That's where the understanding comes from, that's where the intuition comes from, and it absolutely is a skill that I will be testing on exam 1. Exam 1, don't panic, is not next week, it's going to be the week after next, and I'll release the study guide for exam 1 as soon as we finish section 3.2. All right? Okay. I've got to head out because I have another class that starts in about 5 minutes. Are there any urgent questions before we wrap up for the day?
Yes, office hours today?
Yep, normal office hours today.
Okay.
Any other questions?
No, thank you.
Grayson, the study guide I will release next week after we finish 3.2. Study guide's not out yet. I'll release it next week. For now, just work on the homework, right? The homework is the best way to prepare yourself for the test. Solve the homework problems, solve them honestly on your own without any outside help. And then the study guide will come next week. All right, I hope you guys have a lovely rest of your afternoon. You can come visit me in office hours today. Otherwise, I will see you on Friday.